Okay, in this particular video, we are going to now finish the final of the three Exergy problems. This particular problem is a closed feed water heater consisting of two streams. Both are water or steam. The first stream is coming in at 1.1 megapascals and 200 Celsius, and it leaves as a saturated liquid at the same pressure. And then the other stream is feed water that comes in at 2.5 megapascals and 50 degrees Celsius. And it's an isobaric process such that the temperature rises until it gets to 12 degrees below the temperature of the steam. So as the steam goes through and leaves as a saturated liquid, there is a temperature associated with that. And so this final temperature is 12 degrees Celsius below that. Okay, so with that in mind, we go back to our map of thermodynamic calculations. And this is a open system. It's a feed water. It's a non-mixing multi-flow system. In this case, both of the fluids are PC model. And so we're ready now to go ahead. We're not, in this particular problem, we are not asked, we are asked to determine the exergetic efficiency of the heat exchanger, so we do have to assign a dead state. The dead state's 10 kPa and 25 degrees Celsius. And what we're after is the ratio of the two mass flow rates. And so we're not told which one or how much one is versus the other. We're just looking for the ratio of the two mass flows corresponding to a first law enthalpy balance. And so we go and we pick our dead state, 100, and it was 125 Celsius. Okay, we're now ready to put in our first state, and our first state comes in at 1.1 megapascal and 200 Celsius. So 1.1 megapascal and a temperature of 200. Check that out. Okay. 200 Celsius. And then it leaves as a saturated liquid. So it leaves, so we've gotten state 1, and we see that it's a superheated vapor. And for the purposes of the calculations, we're going to go ahead and assign this first stream with a m dot equal to 1. And now when we go to state 2, we're going to say that the m dot is equal to the same thing. And what we know about stream 2 is that it was, go back here, it was at the same pressure. So we know that it's a saturated liquid at the same pressure. So at the same pressure would imply that pressure 1 is equal to P1, and we know that it's saturated liquid, so it has a quality equal to 0. And so this is then the two thermodynamic properties that we need to define the state of that fluid. Here's the m dot. So we've got the state of that particular fluid. If we were to look at the graphics panel at those 2 points, we have a superheated condition at the same pressure. If I were to draw a constant pressure line through, we would see that that's the high pressure of the superheated fluid and comes out as a saturated liquid. And now we're ready to go back to then state number 3. This is the other fluid, and the other fluid we recognize is going to come in at 2.5 megapascals and 50. 2.5 and megapascals. And so 2.5 and 50 degrees C. And we see that those two conditions, because of this high pressure and this relatively low temperature, it comes out into the subcooled liquid. And now in this particular case, we don't know m.3. Okay, so we're going to leave it blank. But what we do know, when we go to state 4, we know that state 4 has the same pressure as state 3. And the problem said that it comes out at a temperature, let's read that again, at a temperature 12 degrees lower than the exit temperature of the steam. And so it comes out at T2 minus 12. So whatever that corresponds to. Okay, that's that temperature. So temperature 2 was 184 Celsius. And so temperature 4 is actually 12 degrees lower than that. So we have the pressure, we have the temperature, and again, we know that the m dot is equal to m.3. And so it stays white because it hasn't been calculated yet. And once this is calculated, then it will show up here too as m.3. And so we've got all of our states. If we go to our device panel or our graphics panel, we could see then that the other states are shown there. 3 and 4 are real close here because they're in the subcooled region. We now go to our device panel. It is a multi-mixing, a multi-fluid non-mixing, open and steady. And in this particular case, then we assign the states. And to assign the states, then we say state 1 coming in, state 2 going out. That's the one stream. And then here we have state 3 going in and state 4 coming out. And so now it knows that there's these two streams that are talking to each other, communicating thermally between. And so now it's going to balance this equation here, this energy equation. We know that there is no heat transfer and there's no work that is going on. When I say no heat transfer, there's no external heat transfer. All the heat transfer is going from one stream to the other stream. In essence, what's happening is this superheated steam is actually going through here and heating up that liquid. And so this is a feed water heater that we'll see in Chapter 8. And so with that in mind, we now can go back to the state panel and we then find that it has now calculated the m.3 and m.4. And so the ratio of the two mass flow rates is 3.93. And so again, it shows up on both state 3 and state 4. What else were we asked? We were asked then to determine, we determined the mass flow rate ratio, and now we're interested in the exergetic efficiency of the heat exchanger. And so what we're interested in is determining for this heat exchanger how much of the exergy that was lost by one stream was picked up by the other stream. And so in order to calculate that, I'm going to go ahead and do a super calculate. And in my I/O panel then, I'm going to set up I'm going to calculate a couple of terms. The first term I'm going to calculate is the exergy that was that was lost from the first stream. And so I'm going to call that, let's just say E1, and it's going to be equal to m.1 times then the difference in the two size. Okay, we're dealing with flow exergy here. And so it's the final, it's the initial, which is the higher value, minus the lower value. And so the size are in kilojoules per kilogram. The m dot is in kilograms per second. And so this is going to be a value. Whoops. Okay. What I did was I made a mistake and used the value of, this E1 is a state, so I have to call this something like X1. And because it already had an E associated with the the energy of a state. So I have to call it something unique. And so X1 is then 710 kilowatts of exergy that is coming out of that first stream. And now if I now calculate a second X, I call it X2, EX2, M dot 3, which is the second stream's M dot, and now I know that it's picking up exergy, okay? And so I'm going to go ahead and in order to make this a positive number, I'm going to realize that it's going to be the higher value minus the lower value. And so we see that 446 is picked up by the other stream. And so my efficiency, my second law efficiency, I can call it a second, is now equal to just X2 divided by X1. And so my second law efficiency is simply 62.8%. And so 62.8 of the exergy that was that was lost in that upper stream was picked up by the lower stream. And we would like to have it all, picked up there. We'd like to have a full conservation of exergy, but there is irreversibilities associated with heat transfer. And so we've then solved this last problem here, is that we've determined the exergetic efficiency of the heat exchanger. And that finishes up this third problem.